Okay, well, let's get started. We have a two for one, two for the price of one this week. I am pleased that we have Professor Marshall Burke and Dr. Sam Heft-Neal from the Center of Food Security and the Environment. And I read a little in their abstract, so I'm excited. They're going to demonstrate, I believe, how to use a combination of both ground sensors and satellite measurements to understand both outdoor, indoor exposure to wildfire smoke. So looking forward to their presentation and hope we have a great discussion afterwards. And I don't know who's going to kick us off. Are you guys going to tag team? So Sam and Marshall, you guys can take over.
All right, awesome. Thanks, Derek. Yeah, I'm going to kick us off. I'm the warm-up act, and then Sam's going to show you the new cool stuff. So let me share my screen here. All right. Folks see that all right? Mm-hmm. Good. Okay. So yeah, our hope today is to walk you through, I guess, fairly quickly, some work we've been doing with a number of excellent co-authors here at Stanford and elsewhere, listed at the bottom. And Jeff, Jen, Ginny, Jessica, God, Jesus, all J's, Michael Wara, thinking about how we can come up with better measures of ambient outdoor exposure to wildfire generated pollution, and also to understand how that pollution infiltrates indoors. So I would say most of the focus so far, and there is a very active literature on the first part of that, much less understanding of the second part of it. This is something we've been working on a lot lately. Sam will talk about that. And it's really important, as we know, because we're sitting inside our houses nearly all the time now. And so really our personal exposure is much more guided by our indoor environment than what's happening outdoors. So we're going to try to show and understand how those two things are related, and do that sequentially. So first, I'll take you through our efforts, first part of which was published, but we're also still working on this to, again, try to quantify at sort of large scale how changing wildfire risk is measurably contributing to surface level concentrations of key pollutants, particularly PM 2.5. And then again, we'll look at how that infiltrates using some cool new data that Sam has done an awesome job putting together. Okay, so big picture here, and these are some plots from a paper we just had in PNAS a couple months ago. So this is the background overall for key pollutants in here. Again, today we're going to focus on PM 2.5. I don't think needs a lot of introduction for this crowd. Small particles that get down deep into the lungs, cross into the blood, do bad things throughout the body. So the background of this is quite good. PM had been declining pretty substantially across the US. Each line here is a different region in the US. We've highlighted the West and the Northwest. So thanks largely to public policy, the Clean Air Act in particular, air quality had been improving across the country. And then if you sort of blur your eyes, you can see this flattening out in the last 5 or 10 years and really reversing particularly in regions in the West. So we don't have 2020 on here yet. The 2020 numbers were, as we know, pretty high in the West and the Northwest. And so depending on sort of your analysis of this very short time series, these air quality gains are either stagnating or they are pretty clearly reversing in parts of the country. Okay, so what's driving that? So wildfires is obviously one thing that could be driving that. We want to be quantitative about their contribution. So we know wildfires are going up. This is burned area. Overall, again, these 2020 numbers, I think, are almost complete. So California was off the charts. In the West, 2020 wasn't. It was sort of right on trend rather than supremely bad, but things are getting worse in terms of burned area. And not surprised, the frequency of wildfire smoke is also increasing. So this is a measure of smoke days. This is a satellite-derived measure, just telling us whether there is a smoke plume overhead. Tell you more about the smoke plumes in a second. I think folks are familiar with some of these data. And as you get more fires, you get more plumes overhead. No surprise. You get some pretty big jumps. So 2012 had a lot of plumes overhead, and some regional variation, but around the country and not just in the West, we see a pretty steady increase in the number of plumes overhead. Okay, so today what we want to talk about is to take those data I just showed you, the sort of motivating data, and try to say something quantitative about how wildfire risk is changing ambient air quality across the country. Number two, we want to try to characterize who is actually exposed to these changes in ambient PM. And we find some gradients in exposure that are actually substantially different from the standard environmental justice gradients that we see for other sources of PM. That is, I think, interesting and has not been shown so far. And then finally, I'll turn over to Sam, and this is then I think maybe the most exciting part is estimating these indoor exposures, how things infiltrate indoors, and again, how that might be related to socioeconomic or demographic characteristics that we care about. So that's ongoing work. Okay, so part one, ambient air quality. The typical way this is done, and most papers in the literature, I would say, do some version of this. They use a chemical transport model or an atmospheric dispersion model, some sort of physics or chemistry-based model to link source and receptor, to link a wildfire that's spitting out pollutants of some sort to people somewhere else who might be exposed to those pollutants. So there are many flavors of this, CMAC, Geoschem, WRF, there's particle tracer models, high split that get used for this. And these models have some substantial advantages. They link source and receptor in very quantitative ways, right? You prescribe where the wildfire is happening and what it's spitting out, and then the model tells you where that stuff goes, right? And so you can at least quantitatively link those two things. They also have some major disadvantages. They have, at least historically, were very computationally expensive. And so modeling groups did not tend to run them over very long time series. And so that made it hard to characterize then using these models, these broader questions about how decadal or multi-decadal changes in wildfires are contributing to air quality. And more importantly, it turns out wildfires are actually quite tricky for these models. So you have to get the plume injection height right, and the model output depends heavily on that plume injection height, and that turns out to be hard to pin down or constrain empirically. And even more importantly, it turns out the emissions inventories, the stuff you feed into the model, saying, right, the prescribed input, basically, these are all over the place. And so a very sobering paper looked at this carefully a couple years ago. And basically what they did is took the same model that gets used all the time, CMAC, and they fed into it 3 different emissions inventories. So you're holding the model exactly constant. All you're doing is changing the inputs, right? And these are 3 leading sort of inventory estimates. And then what they did was model then the concentrations of PM 2.5 in ozone resulting from, again, holding the model fixed, but feeding in different inventories. And if you just look down the left column of maps here, this is the estimated PM contribution from wildfire in 2011. And you get massive differences, again, just based on the inventory, right? 3x differences in national attributable PM 2.5 and much, much larger regional differences, right? Up to 20x differences locally. So this is a big problem, right? So these estimates then we know are going to be exquisitely sensitive to the inventories on which these models are run. And there's disagreement about which inventories are correct. Okay, so we're going to take a very different approach. Yeah.
Marshall, I have a very just ignorant question. So can you explain a little bit more about emissions inventories and define what those are? I'm not very familiar with that term.
Yeah, so these are inventories telling you, so again, these chemical transport models are going to take emissions as input, right? So emissions not just of wildfires, but of all sorts of other things. And then they do the chemistry and transport and then spit out concentrations downstream. So here, these different inventories basically tell you the amount of different particulates or different inputs emitted by wildfires, right? And so we are interested both in, if it's the case of PM, it's the primary PM, and then it's the PM precursors that could be emitted in fires and then form particulate matter through atmospheric chemistry that then gets carried somewhere else. So it's basically just defining the set of things that a wildfire is putting up in the air that's relevant for the concentrations of pollutants that we want to measure downstream. So NEI is the National Emissions Inventories. This is the one sort of the government uses to determine various regulatory things, including attainment under the Clean Air Act, and then the other ones, GFED is one that gets used a lot. It's global. So yeah,
Wow,
different takes
that's
on
really
it.
striking then. That's really striking.
That's right. Yeah, these are large differences. Okay, so we're going to do something different. We are going to try to infer concentrations statistically using a combination of information from satellites and from ground data. So here's a picture of the West on August 19th, 2020. Many of us were here, and it was very smoky in California. Not quite as smoky in San Francisco on that day, very smoky elsewhere in California. And here you can very clearly see these plumes and delineate them from clouds, right? They look different visibly. And often we're looking at these with satellites that give us a lot more information beyond the visible spectrum that help us distinguish smoke from clouds that could look like smoke. So one derived product from these satellite images of smoke are these segmented smoke plumes. And this is done by a group at NOAA who has been doing this now for about 15 years. And basically, they have a set of highly trained analysts who look at these maps throughout the day. They're actually not using Sentinel, they're using geostationary weather satellites. And they hand label plumes throughout the day. And they do this multiple times per day. And literally they're looking at these maps, and then they have a tool that basically hand labels and hand segments these plumes. And what they do then is they generate basically what's shown here on the right, a plume map for a given day. And this tells you where the plumes were on that day. And it also gives you some pretty coarse information about the density, the estimated density of those plumes. And this is from HMS, is the NOAA group hazard mapping system, hazard mapping service, I forget the S. Hazard mapping something. And so these are generated near real time. So these could have issues, right? You could imagine there could be issues especially when it's quite cloudy, how well can we segment? But this is sort of the best we have in terms of an off-the-shelf segmented smoke map. So we're going to use these plumes to try to, again, say something statistically about how variation is changing. So just to show you how much variation there is, these are plume maps. This is an animation we made in 2018, a very smoky year, and just showing you the wildfire plume activity across the US. You can see as we get into the summer here, June, you start seeing a lot of fires in the West. It's really going to start blowing up. Here you go in August, massive plumes, fires in the West and fires in Canada. Now it quiets down. And here you'll see the campfire in a couple seconds. There it goes, right? So tons of variation, both spatially and temporally, in terms of who is exposed to what, at least as measured by these plumes. Okay. So basically, we're going to take these plumes and estimate statistical models that relate having plumes overhead to ground measured PM, right? And what's nice about that is it doesn't depend on getting emissions inventories right, getting the chemistry right, anything at all. This is just a statistical relationship. It's very straightforward to fit these models. It's very easy to test them out of sample. So you can train them in one area and validate them somewhere else on data that the model has not seen. We like that. So that's good. It has some disadvantages, though. It's hard to link source and receptor. It's hard to know exactly what fire the plume is coming from if there are a lot of fires active. That's something you care about. That could be a problem. It's very hard to know where the smoke is in the atmospheric column. This is actually pretty important. So just having a plume overhead doesn't tell you if the smoke is mixing down to the surface or not. And that has a large effect on PM. And again, these plumes are hand drawn by humans, right? They could have mistakes. And to the extent that they have mistakes, some of that measurement error will be not incorporated, but it could be a problem in the statistical analysis that I'll show you. If folks want to talk more about that, it has specific statistical properties that we can think about, but it's something we need to think about. Okay, so basically what we do then is, again, fit statistical panel regressions relating having plumes overhead to ground measured PM. Here I'm showing you fairly aggregated data. So in this initial paper, we're trying to say something about the decadal contribution of wildfires to PM. And so we've aggregated up to an annual level. So each dot here is a station year. So we are comparing ground measured particulate matter at all of the EPA stations in a given year. We're comparing that to what we predict from this statistical model in terms of what the PM was that year. And this model looks pretty good, actually. We can explain about 60% of the variation in ground measured annual PM out of sample, right, on data that the model was not fit on. And this equals or exceeds pretty much any of the published models that we could find, either the statistical models, of which there are few, or really these atmospheric chemistry models. So to us, this looks pretty good, and it's very tractable. Okay, so if you believe that model, then we can sort of do things with it. One thing we can do is generate maps like these. So this is the estimated smoke contribution to overall ground level PM 2.5 across the US. Our plume data start in 2006, so we can't go back further than that, unfortunately. So here are two maps. This would be early in the measurement period and then later in the measurement period. Again, this paper only goes up through 2018. We're updating it to 2020 now. It's not ready yet. But basically, you can see sort of what we had already suspected is that the contribution of wildfires to PM is going up pretty dramatically. This is measured in units of PM, micrograms per cubic meter. But basically, you've seen this go up pretty dramatically, and not just in the West, right? You see pretty large increases in the Midwest, and the northern Midwest in particular, where you get both fires from the US and fires blowing in from Canada. And also in other parts of the South. And this actually, what we struggle to fully distinguish here is wildfires from prescribed burns. The plumes are going to pick up both. The Southeast has done a lot more prescribed burning, and so some of this effect might be from changes in prescribed burning. No, I see you have your hand up. You want to?
Yes, that was on purpose. It is not always, I realize. So looking at those maps, some of the sources seem fixed, and I can imagine ways in which there might be. Maybe there's something in Central Florida that burns regularly. Is this an artifact, or you know, I'm seeing that the intensity is different between these periods, but the patterns are very similar, and I can imagine ways in which the patterns might be consistent. But I guess I'm wondering if it's an artifact or if that is the signal, in fact.
And you're thinking about the animation I showed where it looked like some of the sources were fixed. Is that what you meant?
No, I'm just saying, looking at A and B on the screen right now.
Oh,
it seems like there are a number of places where you're getting essentially the same sources in the two periods, but that the values are higher.
right.
And I guess I'm wondering if the sources are in fact that fixed through time, spatially.
Yeah, I mean, part of it reflects where forests are and where forests are likely to burn, right? So in the Pacific Northwest, like along the coast, like you get pretty low levels there, you get a little bit higher, but those forests typically don't burn that much. Same thing, you know, Arizona, you don't get a lot there. You start to see some of this range of mountains, if you guys can see my cursor across Arizona. So I think a lot of it does reflect the fact that there are forests in some places that burn more. Southern Colorado, you don't get that many fires because traditionally have been too high alpine. Now you get a little bit more, right? So I think they are fixed at this scale in the sense that this is just reflecting, you know, where forests are that burn. This part in the Midwest, I don't have a good story there. There are some parts of Arkansas where I grew up that do burn in the Ozarks, and so that's, I think, part of this. You have a lot of deciduous forests there that burn. Yeah, so I think it's not what one concern would be. We're mistaking forests for something else that generate plumes. I think the more likely explanation is this is where forests are and they burn more.
Okay, thanks.
Yeah. Okay, so then we can finally take these models and run some counterfactual. So what would have happened had the wildfires not increased, right? And from that, we can estimate, okay, what was then the overall share of PM 2.5 attributable to wildfires, just by subtracting out that predicted amount from wildfires. And basically, you see that on the lower left, that's the predicted percent of PM 2.5 from wildfire smoke. And again, this has gone up sort of everywhere in the US, but specifically quite quickly in the Northwest and West. And in recent years has contributed maybe half of the overall PM 2.5, right? And that's like in years like 2020 or 2018, where you get very, very intense wildfires for over a month, such that you can really start accounting for a lot of the PM, right? So these shares are massive and they're up dramatically. So this is roughly doubled since we began observing it in 2006, right? So the back of the envelope take home is wildfires have roughly doubled. Wildfire PM has roughly doubled over this period, and the contribution of wildfire to overall PM has roughly doubled. That's a lot. Okay, so who's exposed? If we have these measures of wildfire PM we trust, we can then combine them with socioeconomic or demographic data we have on the ground to understand who's exposed. So let me show you some quick plots on this, first in California and then as a country, across the country as a whole. So here's looking at California. Nice maps made by Sam. Mine would be uglier. So on the left here is the map of overall PM 2.5. It's bad in the Central Valley. LA is better, but still bad. So we sort of know what that map looks like. On the right is the smoke day is just the satellite-based product, right? Smoke tends to happen in other parts of the state, not in LA. It's in the Sierras. It's in Northern California. And so now what we can do is we can translate that to actual PM, and then we can see again how the PM exposure differs by groups we care about. So here's the relationship for overall PM. This is again all sources of PM. In this data set we work with in California, where we have very detailed information on sort of household level information on demographics and race. This is what the standard plot looks like. So here we have, this is split up by race, ethnicity, and by income. And so as you move down, you get richer. And then as you move across the columns, it correlates with the race or ethnicity. And the colors then correspond to the average exposure. So here's the map or the sort of relationship we're used to looking at. So lower income communities tend to be more exposed, but even conditional on being lower income, racial or ethnic minorities tend to be more exposed, right? So Hispanic, non-white Hispanic, and Black communities tend to be more exposed. So this is the standard sort of environmental justice picture. Smoke actually looks quite different, at least looking at California here. So it turns out that majority white populations tend to be more exposed on average to smoke-based PM than Hispanic or Black populations. I think that's just a function of where people tend to live. But it reverses the gradient, right? And similarly, there is an income gradient, but it's not nearly as strong as what we see in overall PM. So basically for this growing, increasingly important source of PM, it has a very different distributional story than what we're used to thinking about when we think of overall PM 2.5. Here's the national picture. Here's the relationship between overall PM 2.5 and basically the percentage of people in a census block who are white, non-Hispanic white. And again, whiter populations tend to be on average less exposed to PM 2.5 by a couple micrograms. For smoke, it goes the other way on average. So whiter populations tend to be more exposed to smoke-based PM on average. So our conclusion then from this as wildfire becomes more important, a more important source of PM 2.5, it could actually change some of the environmental justice intuitions or gradients that we're used to thinking about when we think about overall PM 2.5. Okay, in outdoor. Now I will hand it off to Sam, who's going to tell us ongoing work about how changes in outdoor pollution actually translate to indoor. And Sam, do you want me to exit and you share, or do you want me to just?
You want to just keep?
Sure.
Yeah. Manage the shit. Great. Thanks.
Sure.
Okay. So great. Thanks. As Marshall mentioned, I'm going to talk quickly about the indoor work we've been doing. So normally, when you think about a health study or some study where you care about what people are exposed to, the way we assign pollution to individuals is by looking at the nearby ambient pollution measurements. But we know that actually most people spend most of their time inside. So this is data from the American Time Use Survey. On average, most people spend more than 70% of their time indoors. So what we care about really is what people are being exposed to a lot of the time when they're indoors. And this varies a lot by group. So again, this is splitting out the time use survey data by group. And one that I want to highlight is in the top right. If you look at the age split, then we know the people who are most vulnerable to PM 2.5 impacts are people 65 and up. as well as children and pregnant women. And for people 65 and up, they're by far the most likely to spend time inside. So if you want to assign the correct exposures to people in that age group, then we especially want to know what's going on indoors, not just outdoors. And then by season and by race and ethnicity, it varies some, but not as stark as the age, and also income, lower income people spend more of their time at home.
And this does not have 2020 in it. Of course, we were all at home in 2020. This is just through 2019.
Right, that's a good point. So one way for us to look at how much stuff from outside gets inside is to use these low-cost purple air monitors that a lot of people have been using recently. You're probably familiar with them when we're checking the air quality. They're a lot more common than EPA monitors. They give us a much better spatial distribution. And then also there's a combination of indoor and outdoor monitors. So here is just showing the places where we have both indoor and outdoor purple air monitors. And so with this, we can actually estimate when pollution changes outside, how much does that affect pollution inside? We have about 2,500 indoor monitors that we're able to match to outdoor monitors. And then we have hourly observations for all these data. So we end up with about 23 million monitor hour observations. And so to give you an idea of what the data look like exactly, I have an indoor monitor at my house. So this is my daily PM exposure for the last month. The navy is the exposure in my house. And then the library around the corner from my house, about 300 meters away, has an outdoor monitor. So that's showing the red line. So on average, you can see that my indoor pollution goes pretty much in line with outdoor pollution, but it tends to be lower, with the exception of one Saturday where we did a ton of cooking inside. And I was able to actually get my indoor PM 2.5 average higher than the outdoor for that day alone, which was, a big accomplishment.
Good work.
So
Good work, Sam.
Other than that, you can see that we tend to have much lower peaks, but it moves really closely together. And so we use a regression model to relate the outdoor and indoor monitors, both with contemporary outdoor pollution, contemporaneous, and then also with a bunch of lags. And we add those up to get this average effect for how much 1 microgram increase of outdoor PM 2.5 increases your indoor PM 2.5. And you can see there's a huge distribution of estimates. So this is showing the distribution across monitors. Our average estimate is about 0.2. So it's just a 1 microgram increase of outdoor pollution increases indoor pollution by 0.2 micrograms. But you can see there are some monitors that are as high as 1. There's going to be, we'll discuss a little bit more, but there are a bunch of reasons why you have this variation. One is going to be physical differences in housing type, but it's also going to be a combination with behavior. If people leave all of their doors and windows open all the time, then you're going to have a much higher infiltration than the exact same house with windows and doors closed all the time. Next slide.
Sam, this is for one house or for a bunch, for all observations?
This is showing the distribution across 2,500 different houses.
And some had some sort of air filtration going on?
Absolutely. So that's a great point. I didn't mention there's a tons of reasons why you could have a high or low infiltration. And a specifically important one is going to be whether or not you have an indoor air monitor or indoor air filter. We don't observe that, but you would expect that the ones that are close to zero are ones that are filtering air out, filtering dirty stuff out. And then you would expect, you would estimate a lower infiltration rate then, because I guess the stuff is getting inside, but it's not getting to the indoor monitor because the air filter is actually sucking it out.
And sorry, you want questions at the end or should I ask them now?
You can ask now.
Yeah, do you have, I guess, given that you have the location of the monitors, you kind of have an estimate of whether this is a high income or low income houses, though the monitors themselves will be biased in terms of locations. So
yeah, that's where we're going next.
Okay, yeah.
Sam, you don't mind, I'm gonna piggyback onto that, this really cool plot here. I'm wondering, is there any bias associated with people who would tend to buy a purple air monitor being more likely to run an in-home filtration system?
100%. This is definitely not a representative sample of the American public. There was just a paper that came out a couple of weeks ago showing that the co-location of purple air monitors is not representative of either the income or the PM distribution of the overall US public. So that's definitely something to keep in mind when we're looking at these results. But again, so we can see how the infiltration rates vary with different factors. And again, this is going to be picking up, I think, mostly behavior. So if you look at the temperature response on the left-hand side, as temperatures get higher, infiltration rates go up. So that's consistent with the behavior where when it gets hot outside, people open their windows. Most people in California don't have air conditioning. So if you use window opening as your way to moderate heat, then your infiltration rates are going to go up as it gets hotter. We don't see a huge difference across seasons, although we do see the lowest infiltration rates in winter, which again is consistent with people keeping their doors and windows closed more often. And then I think an interesting finding is that if you look at how infiltration varies with PM level, outdoor PM level, we see the highest infiltration rates at the really low PM levels, which suggests that when PM gets really high, people become cognizant of this effect and they start either turning on their air filters inside or keeping their windows and doors closed, but making an effort to reduce infiltration. And so you can see that point on the far right, when PM is over 100, it's our estimated infiltration rates are less than half of when PM is below 10. So one of the reasons we care about this is because we want to know specifically about whether the infiltration varies during wildfire events, and then how does this matter for what people are exposed to in terms of wildfire smoke. So we can look at a specific wildfire event in California to see what the indoor monitors look like. Next slide. So we took all of the monitors that we have in the Bay Area, and here's the location where we have both indoor and outdoor monitors. And then we split them into the bottom 20 percentile of infiltration rates. So these are the monitors we think that have the lowest infiltration. And then these are the monitor that we think have the highest infiltration. And then we can look at how the exposures vary for these two groups. So we plotted the PM both for outdoor and indoor. Each line here is an individual outdoor monitor, and then the bold line is the average. So these are again for the low infiltration households. Then if you look at the high infiltration households, you can see that our outdoor PM exposures are basically the same, regardless of your infiltration rate. But once you start to look at the indoors, you can see that for the low infiltration households, on average, PM continued to be below 30. But for the high infiltration households during the really bad day, like September 12th, the indoor PM went up to above 100. So the implication is that when we think about what people are being exposed to during a wildfire event, it's going to depend a lot on household infiltration. And if you live in a low infiltration household, then you can adapt or you can change your behavior in a way that your infiltration is really low. But if you live in a high infiltration household, whether that's through behavior or through physical structure, then you're going to get exposed to a ton of really bad stuff even while you're inside. So as we were discussing, we think that there are a bunch of reasons why you would expect to have different infiltration rates. There's some work from engineers at Lawrence Berkeley Lab that suggests that housing age and quality are an important factor. So older houses tend to be leakier. Income as well, especially with the response of buying expensive filtration. If you have an air filter inside, that's going to reduce your infiltration rate by a lot. And then we would expect some differences potentially related to these factors with race and ethnicity, especially historical redlining that led to differences in housing quality. And so we would expect the lower quality housing that certain groups have been forced into is going to have higher infiltration rates. But that work's underway. So we've developed those models. We don't have full results yet, but it looks like there are some differences, but potentially because there's differences in both housing structure and then also differences in behavior, we're trying to figure out how to tease those out separately. And it seems like the behavior matters a lot. So maybe the differences in housing structure aren't as big as we thought. But we're going to continue doing this for a number of reasons. We think that it's going to be important to help understand disparity in health impacts. Infiltration is a potentially omitted factor that could maybe help explain why some people have much worse outcomes than others. And then it's an empirical issue if we're just mismeasuring exposure differentially for different groups. If you think about the cost benefit analysis of whether or not to weatherize your home or to do energy efficiency upgrades, this is a potentially big benefit that is not currently going into those calculations, where if you put in new windows that reduce infiltration, that could potentially have a huge health benefit in addition to lowering your energy bills. and then suggest different policy interventions. If infiltration is a big factor, then either subsidizing low-income houses to have energy efficiency upgrades or providing free air filters. There's a number of different responses that you would think, different interventions that you could imagine if household infiltration is one of the big things that's determining the differential exposures. And so just to summarize everything we've talked about, so wildfire is quickly becoming a key contributor to air quality. We're seeing it contribute something like double the overall amount of PM that it was contributing 15 years ago. And then we see big socioeconomic gradients in outdoor exposure to smoke PM that are quite different from the overall gradients in PM that we are historically understood. And people spend most of the time indoors, but we don't have a great understanding of how infiltration works. But it appears to vary a lot, which is a potentially really important factor in understanding the health disparities from pollution. And with that, we're happy to answer any questions.
That was fantastic, guys. Really a great presentation and a lot of things to be thinking about. So yes, let's open the floor to questions. Avery? Oh, the clap, sorry. It was applause.
It was the picture at the beginning. Yeah, it was a Rowan from Oregon. I should have cited that photographer. Yeah, it was a couple years ago in Oregon. It's favorite photo ever.
Yeah, every cover of every wildfire presentation we give.
Yeah.
Bruce.
Well, great work. And I don't know whether this is reassuring or not, but we found something similar using survey data. IRIS overlaid the smoke data on top of, and also proximity to the fire. And we did discover a couple things that conform with what you found, which is that the usual racial difference isn't there. But the interesting thing, and you think about this politically, is that in your chart, as I recall, Marshall, you have white lower income people as having a heavy exposure to it. And those, of course, are in the rural areas, the Trumpistas. And one of the things we discovered, it was kind of shocking when we first saw it, is that there seemed to have been a denial mechanism such that Republicans were less likely, given the same level of exposure to smoke, to notice the smoke. So it's kind of like the COVID denialism. So it's kind of interesting that that's going on. Obviously, I don't, whether Mary and Carrie aren't on here, but I mean, I think one of the things we're trying to do is to sort of refine this down to what goes on at the micro level in terms of people using masks, or remember, you got different regions going on here. You've got people in the Central Valley that have higher temperatures, have to have air conditioning on. Then if you layer on that you're going to also have air filters as well as air conditioning, you know, you're starting to get into you know, an additional expense. And ESHA's actually looked at the subsidies that we give to low-income people through the CARES program. But the reality is that they largely, and ESHA, you can correct me if I'm wrong, but I think they largely stay within the lowest tier of use. So if you're going to push them out of that by having air filter systems, that's going to be a problem. So I do think tackling this in terms of getting people to actually wear masks, or to do the hardest thing, you know, I've seen this over and over again with our adaptation stuff, is that it's easier to start with new structures. How we go about finding the funding and the political will to rehabilitate existing structures is a real tough one. I mean, Jenny Sakali was talking about this with respect to the work they're doing on the Bay in terms of flood, but I think it occurs with all these things. It's just going to be harder to do and to find the money to do that. And so I do think as we get into a more defined, targeted look at these different populations, we're going to have to be very creative. I think you had some great ideas about what we might want to do, but where we find the money and how we adjust to the different types of housing, the different differential use based on ideology or education, and then the underlying conditions. Now, one thing that I wasn't clear was, I assume, were you subtracting out the underlying air quality problem? Was that ever one of your estimations, or were you just taking the total exposure of PM 2.5? Because you did go through early on in distinguish between what the baseline 2.5 was, and then you did the wildfire. I mean, is there anything in that, or does it all follow from the baseline?
Do you mean when we're estimating the infiltration or the ambient?
Yeah, it's the wildfire. I'm just wondering whether the wildfire adds more in certain kinds of houses. In other words, I mean, the wildfire season tends to occur when it's warm, right, already. So the behavioral interaction would be that you'd be more likely to be stifling. I don't know. I'm just wondering that whether it makes sense to take out that increment, which is the wildfire increment, as opposed to the baseline. So you think of a city like Fresno, which gets all kinds of pollution all the year, but it's actually even worse to get wildfire smoke in the summer. Often of it, by the way, the models, I didn't understand whether you guys were taking into account wind patterns, but I know that when we were looking at it, that some people do that. But what the people in Fresno say is that the prevailing winds bring a lot of smoke down from the north into there, and then it sits in that particular topography there. So, I mean, I think it's great. This is great stuff. I think it's important. And but I don't think we're anywhere near being able to come up with any kind of policy for the state. I mean, we got a lot more work to do, but this is just great stuff.
Thanks, Bruce. Yeah, no, agreed. We're not ready for that either. And basically what we don't have the models ready yet, but Sam sort of teased them so we can have a house level infiltration prediction, right? And then we can try to predict that with observables, and we can actually match houses to CoreLogic. So we don't know the lat long of the indoor monitor perfectly. It depends, people input that themselves. And so some are going to be wrong or random or whatever. But basically we can match as best we can to CoreLogic. And then so we have a ton of household level observables. From census, we have very local level demographics, right? We know a lot about climate. And so we can try to predict variation from those observables. And we can explain maybe 20% of the variation from observables. And this is even knowing, like, I know whether you have AC, right? I have a good guess of your income. I know your home value, like a lot of the stuff that you think would matter a lot. And we explain about 20% of the variation, even in like fancier nonlinear models. So that means there's 80% that we don't explain. And that's probably either unobserved behavior or indoor filtration that's unobserved, right? And so I think you're right that like we would love to be able to explain a lot more of that, but we're just out of obs basically to be able to do it. So if anyone knows how to push surveys to purple air indoor monitor users, like that would be great. Like, do you have a filter? Are you running a filter, right? Like just basic stuff like that would be so helpful to help us understand these differences. Or are we screwing up how we're using our observables, right? Or what is it that we're missing? I don't know. So you're right that we're far from it. There would be a couple key points of data that we would love to have that we don't have. And so would love anyone's thoughts on how to get that stuff.
So
Yeah.
one suggestion, maybe the other way around, we may roll out a survey on just people's usage of items during fire season in California using Prolific. And we can add a question asking whether they have a purple air monitor. So that would include all the demographics data too. In parallel, we won't ask for home value or stuff like that, but definitely whether they have an AC system or an exhaust fan for their kitchen and stuff of that sort. So we can talk more if that's helpful.
Yeah, let's do it. That's great. Thanks, Ness.
Yeah, just piggybacking what was discussed there, I thought, because I've been trying to do some fundraising efforts for our hackathon, I think Mary might have a connection at Purple Air. So I'm wondering, I get spam all the time by product manufacturers, and I don't know if we have enough of it in to say, hey, here's a survey and you're entered into a drawing to get an Amazon gift card, and you might get only 10%, but if you get 10, 20%, that might be enough to do some statistics and better understand your data.
For sure.
And then coming back to what Bruce said, I'm wondering, have you guys thought about disaggregating the data between smoke days and non-smoke days? I know you already have struggles to get a signal of it, but I'm wondering if there'd be a difference between smoke days and non-smoke days in your data for infiltration.
We have done exactly that, and we do see a little bit of a difference, but it seems like the main difference is kind of shown in the PM plot we showed, where when it's a really bad smoke day, then we see much lower infiltration, which suggests that it becomes this event people are really aware of and they act accordingly. But we don't see much of a difference on like a low smoke day where there's smoke overhead, but we don't see much of a difference in PM. What we haven't done is looked at the types of days where, you know, you have very visible smoke, but it doesn't affect PM on the ground. We haven't looked specifically at those yet.
I had my own sort of education on this though too. During the I had an outdoor purple air monitor for a while, and then during the fires, my indoor one finally came, like right in the middle of the fires. And you know, we had been doing a good job. We're trying to close our doors and windows. We have lucky to have AC, right? So I was like, oh, our indoor exposure is probably going to be all right. And they weren't. They were terrible. It was terrible. Like we had levels above 100 inside our house, even with everything closed and the AC running, right? And so I spent $1,000 on filtration, and you can see in the time series, like it immediately then breaks the link between outdoor and indoor. So, you know, my guess is that, at least from my own N=1 experience, like, you know, demographics in the normal sense are not going to explain this necessarily in the ways we might expect, right? There's even among, embarrassingly, someone who like purports to study this stuff, like it was really bad. And I had the money to spend on filtration. So yeah, I don't know. Ryan had your hand up.
Hi, can folks hear me?
Yeah.
Great. Thanks for the presentation. I'm curious to what degree that public spaces were represented in the purple air data set with these monitors, sort of in the light of the fact, you know, our Bay Area Air Quality Management District is really gunning for the idea of community clean air shelters. You know, did you see that? Are trends different? Curious on that public aspect.
So yeah, great question. We tried hard because we wanted to be able to match to household characteristics and demographics. We tried very hard to filter out non-residential homes. So we're pretty sure that, so people, you know, schools have put some of these things in, some community organizations have put these things in. So, and we tried to filter out all of that as best we could based on the lat lawn, based on what people input to their like purple air, what we can see in the metadata basically. So think of this as just residential homes. So this does not directly speak to measurement of indoor exposure in the settings which you're talking about. It might speak to the importance of having those places given high observed infiltration. So Sam, anything to add on that?
No, I think just that's something we'd like to look at, especially, you know, schools and libraries and these other spaces we do have some monitors for. And so I think it would be interesting to look at whether those infiltration rates are very different from what we see in people's homes.
Gotcha. So that data might be out there, but it wasn't part of your.
Yeah, it's a much smaller number of observations, but definitely we see, you know, it's whatever, we definitely see libraries and schools and some government buildings as well.
Great. I think we have a question from Pratik.
Yeah. I'm a bit confused on how, like, on why would you try to see infiltration levels as completely ownership of commodities? I think it might be useful to see them as behavioral changes in actions that people do. For instance, like I guess I saw a couple of I saw a graph where like people who when people saw that air quality rose beyond 100 PM to micrograms per meter cube, they started closing windows. So for instance, if I'm like, if I have more information on what's going on, and if I have any way of observing air quality outside, I might like create very costless behaviors in my life that might make me a high infiltration household. So I'm not sure if like estimating would be the best way to take a look at it, but what are your thoughts on that?
I think that's right. Yeah, I think that's absolutely right. And we see some evidence of exactly what you said. I mean, households do, so infiltration seems to go down. And here infiltration is just a marginal effect of an additional unit outside, right? And so we can measure that as a function of outdoor concentrations. And it does seem to go down when concentrations get high. And we're interpreting that as exactly like you say, some sort of behavioral response, right? Even if we can't observe that behavior directly. So fully on board with what you're saying, I think.
Yeah. So a good policy intervention from that would be that like we can come up with like good interventions to make that change in people's lives that are costless and basically see a good change, see a significant change in how people's well-beings in general.
If there is variation in how people respond at the, which is actually
Mm.
something we could look at, like, do we see differential infiltration at, I mean, it is actually a good idea. Do we see differential infiltration at that really high end, or does everyone respond in the same way? If everyone's already responding, then additional policy intervention on information side won't help, right? But your hypothesis is that it would help, and that would then, for that to be the case, we should see differential infiltration. Yeah, we can look at that. It's a good idea.
Yeah, that's something we can test. Yeah.
Great questions. I just want to let people know, I want to respect people's time. It is 1:22, so I'd like maybe one more question, but people obviously can depart as they need to. But any final question we can ask our wonderful speakers today? Okay, I shut down the conversation, but what a great talk today. Thank you, Sam and Marshall, for your insights and sharing your work. It's really important stuff, so thank you for it.
Thanks everyone for the great questions.
Yeah,
All right,
thanks everybody. Thanks, Derek, for organizing.
Of course, and we'll see you next week. Rebecca Miller is going to enlighten us on a number of things, so look forward to seeing you guys then. Have a great afternoon and week.